Okay, this is part 1 of exercise 1.37. So you've got let u, v, w, x be 4 vectors in R3. None of them are the 0 vector, and I asked some questions that you have to answer. You're not always going to be able to answer the questions, and if you can answer the questions, you have to tell me why you can't. So the first one, part 1, says if u and v are vectors in R3, neither one are the 0 vector. Let me just write it like this. Can every vector in R3 be written as a linear combination abbreviated as lin combo of u and v. Okay, so in other words, can we find for any vector w in R3, can we find a constant a and b such that au plus bv is equal to w? Okay, and we have to be able to do this for every vector w in R3. Okay, that's the question that we want to answer. Can we do this for every vector w in R3? Okay, well really, let's write this in component form. So if u is u1, u2, u3, we could write this as a u1, u2, u3 plus b v1, v2, v3 equals w1, w2, w3. Okay, so really what this gives us is a system of 3 linear equations and 2 unknowns. So immediately the intuition that we should be having, or that we should be developing, should say the following: there are more constraints than unknowns, so we should expect that a lot of times, getting dangerously close on my battery here, a lot of times there's not going to be a solution for certain right-hand sides. There might be a solution for some right-hand sides, but most of the time we should expect there's not a solution just because there are more constraints than variables. Okay, so let's think about this. So that's the intuition. Now we need to take that intuition and make it rigorous. So one way to do this is to just try to come up with a right-hand side for which there isn't a solution. And one way to do that is to come up with a right-hand side for which there is a solution, and then try to alter the right-hand side a little bit so that it is no longer a solution. And hopefully you'll get what I'm talking about in this video, and you'll be able to apply it in similar ideas in other videos. So let's just say a and b are both equal to 1. If a and b are both equal to 1, the left-hand side is u1, u2, u3 plus v1, v2, v3. And then for this equation to be true, the right-hand side needs to be u1 plus v1, u2 plus v2, u3 plus v3. Okay, so now what I'm going to do is just add 1 to the third component. So the third component now is going to be, the right-hand side is now going to be u1 plus v1, u2 plus v2, u3 plus v3 plus 1. Okay, and now can we find 2 constants a and b plus b times v1, v2, v3 that makes this equation true? Okay, now we know if a and b are both equal to 1, the top equation, the top 2 equations are true. But if a and b are both equal to 1, then the bottom equation is not true. Okay, so what does this tell us? If I look at the system, au1 plus bv1 is equal to u1 plus v1, and au2 plus bv2 is equal to u2 plus v2, and the bottom equation is now au3 plus bv3 is equal to u3 plus v3 plus 1. Now, if I look at the top 2 equations, let's just kind of think through what's going to happen here. Well, this is a system of two equations in two unknowns. So let's just try to solve it. Now, this is going to be tedious and maybe a little bit confusing, but just go with me for now. Okay, so the second equation tells me that A is equal to U2 plus V2 minus BV2 divided by U2. Okay, so now we see that we're going to have to break this argument up into a few cases. One case is going to be where U2 is not equal to 0. Okay, so now we're going to have to assume U2 is not equal to 0. Okay, because we're dividing by U2 here. So if U2 is not equal to 0, this is what A is. I'm going to take this expression for A and plug it into the top equation. And when I do that, I get the following. I have U1 over U2 times U2 plus V2 minus BV2 plus BV1 is equal to U1 plus V1. Now I'm going to multiply both sides by U2 and divide both sides by U1. So now notice I'm also assuming that U1 is not equal to 0. Okay, so I'm assuming, let me just record this. So I'm assuming that U2 is not equal to 0. I'm assuming that U1 is not equal to 0. Okay, so what's going to happen here? This becomes U2 plus V2 minus BV2 plus U2 over U1 V1 times B is equal to U1 divided by U1 times U2 is equal to U2. And then V1, this is going to be U2 over U1 V1. This is U2, not, it kind of looks like A2, so U2. Okay, so now what's going to happen? Well, that U2 and that U2 will cancel with each other. And so now if I get the B on one side, I can solve for B. So what I get now is B U2 over U1 times V1 minus V2 is equal to what I have on the right-hand side, which is U2 over U1 V1, and I subtract V2 from both sides, V2. Okay, so what does this tell me? This tells me that B is equal to 1. Okay, of course, this requires that U2 over U1 V1 minus V2 is not equal to 0. Because if that's equal to 0, B can be whatever we want it to be equal to. Okay. So now we have some restrictions. So let me write these restrictions. So we're assuming. So the restrictions that we have are U2 is not equal to 0. U1 is not equal to 0. And U2 over U1 V1 minus V2 is not equal to 0. We're having all of these assumptions, okay? So if B is equal to 1, then you could come back up to this equation for A, plug in B is equal to 1, and this will tell you that A is equal to 1. Okay, so if these assumptions are met, the solution is A is equal to 1 and B is equal to 1. Okay, so let's just recap. If you want to solve this system of equations, in particular, these top two equations have to be solved. And if subject to these purple restrictions here, the solution is A is equal to 1 and B is equal to 1. But then that is clearly not going to be a solution to this bottom equation here, because that's going to tell you that U3 plus V3 is equal to U3 plus V3 plus 1. But that equation is just equivalent to 0 is equal to 1. Okay, so now let's think about what happens when these two cases, when these things are not satisfied. Okay, so when u2 is not equal to 0, or u1 is not equal to, or sorry, when u2 is equal to 0, or u1 is equal to 0, or something else is equal to 0. Well, the thing about u1 not being equal to 0 and u2 not being equal to 0 is a little easier to deal with. So let's just come back up to these two equations and see what happens when u1 is equal to 0. So what happens when u1 is equal to 0? The equations become, the top two equations become au1, which is just 0, bv1 is equal to v1, and the bottom equation is just going to be au2 plus bv2 is equal to u2 plus v2. Okay, well, what does the top equation say? This equation tells us that either v1 is equal to 0 or b is equal to 1. Okay, so if b is equal to 1, we can now bring it down to this equation. So this gives us au2 plus v2 is equal to u2 plus v2. Okay, so now I can cancel v2 from both sides, and now I have au2 is equal to u2, and this tells me either a is equal to 1 or u2 is equal to 0. Okay, so now a is equal to 1 or u2 is equal to 0. Okay, if a is equal to 1, then the argument just goes as before, because a and b are both equal to 1, so the third equation is not true. Okay, what happens if u2 is equal to 0? Well, if u2 is equal to 0, this equation now, the system of equations now reads bv1 is equal to v1, and the bottom equation reads bv2 is equal to v2. Okay, so so we're assuming now that v1 is not equal to 0, and now we have this equation. Well, this equation doesn't give us any more information. It doesn't give us any more information about b than this equation. Okay, so that kind of handles the case where v1 is not equal to 0. Okay, so now I'm going to stop right here and let you guys go through and handle all of these other cases. I understand it's tedious. That is part of this exercise. There are these sort of edge cases, quote unquote edge cases, that are tedious. There's other ways to organize this work that makes it a little more clear about what's going on in terms of the different values of u1, u2, u3, v1, v2, v3. But one of the things that I'm trying to illustrate here is that we need a more systematic way for handling equations like this, and that's what section 3 of the book, or section 3 of chapter 1, is going to go through. It's going to give us a very systematic way of studying systems of equations like this, where we don't have to come up with all of these subcases. We'll be able to do it in a much more robust way that's kind of less tedious than this. Okay, but I will handle the other subcases. I will let you handle the other subcases. I just really want you to understand this sort of main case that we're assuming, when u1 is not equal to 0 and u2 is not equal to 0, and these other things, what's going on. Other than that, it's just systems of equations,